stat students. All right, so we're going to follow up with our lesson from yesterday with a similar lesson, but now we're dealing with proportions. So every single lesson that we do, we have to make sure that we have a method for dealing with numeric data, which is what we did yesterday, and also categorical data. So we're looking at the sampling distribution of a sample proportion. So that means that we're dealing with categorical data. From here on out, that's one of the big questions you want to ask yourself. Is my data numeric or categorical? So let's do this. If we want to draw conclusions about a proportion of individuals or objects in a population that have a specified property, we will use a sampling distribution of sample proportions. Remember, proportions are associated with categorical data. And so one thing you might want to remember is that categorical data or proportion here is a success, whatever you deem a success over the total. That's how we get that proportion, okay? So remember, we write a proportion as success over failure, okay? A success being the individual or object possessing the property of interest, and a failure being the individual or object that does not have the property of interest. Okay, for our notation, which is really important, we're going to kind of go through with it. A population proportion we denote as pi, and a sample proportion we denote as p. A simple random sample used to obtain p provides an unbiased estimator of pi. So similarly to what we learned yesterday, in other words, the mean of a sampling distribution, which we could say p, is pi, okay? So we're gonna learn some rules just like we did yesterday about these sampling distributions, okay? So it's all about the notation, right? If we're talking about the mean of a sampling proportion, we can write it a couple of ways, okay? So the mean of a sampling distribution for a sample so the notation can vary, okay? We have two types of notation that you can see out there in the world, okay? You can see for a sample, the proportions. We have one type of notation that you might see on your AP stats and on your, and some other stat sites. You might see one type of notation, and then there's a notation that our book uses. For the most part, I stick to this notation that is used in the book because it kind of follows what we already know to be true for sample means. We use Greek letters to represent populations, and we use regular letters to represent samples. So I tend to use this notation. However, either one is accurate. So I'm going to show you both, okay? So for a sample proportion, you can use this set of notation, which is you can say the mean is equal to mu sub p hat or p hat. And either way, those values are going to be the same as the population mean pi. So this is one set of notation that you can use, and the values will equal pi. Just like yesterday we saw, x bar equals mu every single time. Same thing, okay? Okay, your other options is that we can say mu sub p is equal to p, and those values are going to equal the population mean, which is also, or population proportion, which is also pi. So here's your other set of notation. And again, I'm going to use the blue notation more frequently. Okay, even though I use it more frequently, the reason why I show you is because it could pop up. So for your standard deviation, sigma sub p hat is equal to the square root of p times 1 minus p over n. Or we can use this notation where sigma sub p is equal to the square root of pi times 1 minus pi over n. So basically what's happening here is you choose, okay? So you can choose. For the notation in the book, we use pi for a population and p for a sample. And for this other set of notation, we use p for the population and p hat for the sample. So either way, this set of notation corresponds to this. This set of notation corresponds to this, where these represent the population and these represent the sample. And I'm going to use these most frequently. However, it is helpful to know that if you see a worksheet and it has a p hat on it, then we're using this set of notation. It could happen, okay? Okay, so in order for us to make these inferences that the population proportion is equal to the sample proportion, and in order for us to make the conclusion that the sample standard deviation is equal to this equation, there are some conditions that need to be met, just like we had yesterday, okay? So let's go ahead and get those down, what those are. Sample proportions, which is P, have a normal distribution with mean and standard deviation formulas above, provided that these conditions are met. So in order for us to say, okay, the sample proportion is equal to the population proportion and the sample standard deviation is equal to this formula, these 4 conditions need to be met. And before we proceed with any problem, we should check that these conditions are met. So let's go ahead and do this. Number 1, the sample proportion P must be obtained from a simple random sample. So either this is going to be stated inside the context of the problem. Number 1, it's stated. Number 2, it's assumed. Or number 3, based off of the context, it may not be true. So if you see the problem and it tells you that people volunteer for a survey, then we know that the sample was not random. If the information is not provided, we can assume it's random. Or if it's stated it's random, then it is random. Okay. Number 2, these 2 conditions need to be met. N times pi needs to be greater than or equal to 10. And n times 1 minus pi needs to be greater than or equal to 10. Also, the population size, this is a little typo. The sample size is less than 10% of the population size. If these conditions are not met, then we need to proceed with caution. So we've got up here, n is less than 10% of the population. Okay. And one last thing is, how do we calculate a z-score with sample proportions? Remember, z-scores are this standard formula. We've got some kind of value, subtracting off a mean, divided by the standard deviation. So for this set of conditions for proportion, we can just fill this in. Z is equal to some value minus the mean over the standard deviation, which is equal to p minus pi over the square root 1, pi, my bad, not 1, pi, 1 minus pi over n. So that is our z-score formula. Now we're going to take what we've learned previously and just go ahead and apply it. Okay, let's do some problems. We'll do a couple together. Okay. So, number 1, it can be shown that when 2 dice are rolled, the proportion of time that 2 different numbers will result is p equaling 0.833. A sample of 125 random rolls is to be made. The proportion p hat of these rolls resulting in 2 different numbers will be computed. All right, so we're dealing with this p hat type notation here. So we can roll with that. We just have to be aware that it can be fluid. So in this instance, p is equal to the population and p hat is equal to the sample. I want you to be able to work back and forth between either one because your book doesn't use this notation and sometimes AP statistics materials do or don't. So we have to be able to work with either one, just knowing that we can switch them out at any time. But if you're working on your own, you can decide what you're comfortable with. All right, so for this example, we're going to use that mu sub p hat is equal to p. And that sigma sub p hat is equal to the square root of p, 1 minus p over n. So there's our formulas just to kind of refresh us here. So let's do this. It says, what is the standard deviation of the sampling distribution? All right, so first thing we should kind of define what we're looking at here. And for us, p hat is equal to the proportion of rolls resulting in 2 different numbers. So the reason why we use proportions is because this is a success or failure type situation. A success is the 2 dice popping up with 2 different numbers. A failure is that they don't. So we need to be very aware that this is actually a proportion problem. They tell you here, but they may not always tell you. So P is equal to 0.833. That is for the population. We're saying that for every single instance or case, not just a sample, the proportion of rolls resulting in 2 different numbers for dice is 0.833. So let's find our standard deviation based off of that. We're going to use our formula above. Sigma sub p hat is equal to the square root of p, which is 0.833, times 1 minus 0.833 over n, and n is a random sample of 125 rolls. So we can say over 125. And we calculate this out and get 0.033. All right, so now that I have my mean and standard deviation, I can make some conclusions. I can draw some conclusions and make some inferences about this population or about a sample in relation to the population. Sketch the sampling distribution on the left, labeling at least 2 standard errors from the mean. Okay, in order for us to use these normal distributions like it is asking us to do in question B, we need to check our conditions that we are supposed to check. So let's go ahead and do that first. And once we check that those 4 conditions were met, we can use these normal distributions with peace of mind, okay? If we don't check those 4 conditions, we're going to use them anyways, but we're going to proceed with caution, letting everyone know that the results that they get from this may or may not be reliable, okay? So we're going to go to the side, and we are going to check our conditions. I'm going to just make more room over here for this, kind of over here. All right, so let's check these conditions. Okay, the first condition is, eek, The first condition is the sample that we're looking at collected randomly? So number one, is it random? And so we can go look at our problem, and it is stated right here that we have 125 random rolls. So we're going to write down here for this condition that it's stated it is random. Condition number two, we have to follow that formula, n times p in this case. So 125 times 0.833, is that greater than or equal to 10? And it is, so we are good. Step 3, 125 times 1 minus 0.833. Is that greater than or equal to 10? And it is, so we're good. And step 4 is not necessarily something we're going to check because we may not always know the size of the population. It's more of an assumption or like a condition that we are stating that in order for these results to be 100% valid and something that can be really considered and taken seriously, then whatever that population size is, 125 needs to be greater than 10% of that population. So we aren't given how much the population is, we don't know, but these are the conditions and the circumstances that we have checked off under which these results will be reliable. Okay, so now we've checked all 4 conditions. This needs to be done at any time before we feel comfortable assigning means and standard deviations to normally distributed data or distributions, okay? All right, question C. I'm going to move these away because they're in the way now. Question C, it says, interpret this result, find the probability p hat is greater than 0.75 and interpret this as a well-formed English sentence. Okay then. Let's do that. All right, so I want to find the probability that p hat is greater than 0.75. And remember, this is the proportion of rolls resulting in 2 different numbers. I'm going to center my distribution at 0.833 with a standard deviation of 0.033. I don't really care about you labeling out 3 standard deviations. This is just more for a visual, so you get to, an understanding of what you need to input into your calculator. 0.75 is somewhere down here, and we're looking for this area under the curve. We're looking for above 0.75. So in our calculator, we're going to use normal CDF with a lower bound of 0.75, an upper bound of something large like 1,000. Our mean is 0.833. and standard deviation of 0.033. Once you input that into your calculator, you're going to get out 0.99. So we can conclude that there is a 99% chance that 2 dice rolled 125 times will result in 2 different numbers. More than 75% of the time. Okay, and using the z-score distribution is going to yield the exact same value as we get here. I mean, it should actually verify that, but we do always want to practice going back and forth between a standard curve and a standard normal curve. That way, you're comfortable with going back and forth in case you have missing information or in case it makes more sense to use a z-score. So let's just double check and practice writing a z-score using proportions. So we're looking for that z-score. We're going to use our formula, 0.75 minus our proportion mean, 0.833, over our standard deviation, which we found to be 0.033. will give us a z-score of negative 2.5. Remember, your standard normal curve is centered at 0 with a standard deviation of 1, and we're looking at the probability of being above negative 2.5. This kind of helps us because we know a lot about standard normal curves based off of the empirical rule, and we know that based off of this z-score, a majority of the data does lie above this z-score value. So the value of 99% makes sense for us. So we're looking at the probability of obtaining a z-score greater than negative 2.5. And we can use our normal CDF to find that. Negative 2.5, something big like 1,000, 0, and 1. And you're going to get the same answer, 0.99. So it's a check, and it's always a very good idea to go back and forth. Okay, so what I want you to do now is I would want you to do number 2 on your own, and then check back in with this video key after you have done so to make sure you've done it correctly. So pause the video now and do number 2. If you just watch this video and you don't attempt it on your own, that's you going rogue and that's your decision. But I feel like you should pause now, do number 2, and then check back in with the key, okay? Okay, here we go. Let's go over this number 2. Hopefully you attempted it on your own. Pedro Alvarez's career batting average is 0.236. So we can take this to be the true proportion of his at-bats in which he gets a hit. So this is our population proportion. We think of the 500 at-bats we expect him to have in a given season as a random sample, and the proportion of those at-bats in which he will get a hit as a sample proportion p hat. All right, nice thing here is that they defined p hat for you. So p hat is defined right here. As the proportion of at-bats he will get a hit. So we don't have to redefine it, luckily. Okay? We know some things. We know that our population proportion is right here, 0.236. All right. What is the standard deviation of this sampling distribution? So sigma sub p hat, we're going to just use our formula, is equal to p, which is 0.236, times 1 minus 0.236 over our sample, which in this case is going to be 500 at-bats. Go ahead and crunch that out, and you should have gotten 0.019 as your answer. All right. B, sketch the sampling distribution on the left, labeling at least 2 standard errors from the mean. Okay, remember, in order for us to assume that it is safe to use a normal distribution, we have to check our conditions. So let's go ahead and do that. First, I'm going to do it down here. So check conditions. Number 1, is the sample obtained random? All right, so it is, let's see, stated as random right here. We expect him to have a given in a sample season as a random sample. So that is stated. Condition number 2, n, which is 500 times p, which is 0.236, is greater than or equal to 10, check. Condition number 3, n, which is 500 times 1 minus 0.236, is greater than or equal to 10, check. And step 4 is that condition that we just let everyone know that in order for these results to be accurate, we need this condition to be true. 500 is greater than 10% of the population. Perfect. Conditions checked, we feel comfortable with using this distribution now. So we have a distribution centered at a mean of 0.236 with a standard deviation of 0.019. And we're looking to find the probability of p hat being greater than 0.200. So, or being less than, less than 0.200. So, 0.200 is somewhere down here. And we're looking at the probability of being less than that. So we're looking at that lower bound there. So we're going to use our calculator, normal CDF. Lower bound, something large and negative like 1,000. Upper bound, 0.200. Mean, 0.236. Standard deviation, 0.019. And we calculate this up, and you should get 0.029. So how we can interpret this is that there is a 2.9% chance that the proportion of at-bats that he gets a hit will be less than 0.2, and this is out of 500 at-bats. Kind of wordy, but that works out. All right, now just for this sake, you don't have to do this every single time. You don't have to use a normal curve and a standard normal curve, but we're going to, just for practice sake, we want to calculate up that z-score for this distribution centered at 0 with a standard deviation of 1. Your z-score should be your mean, or your x value of 0.2 minus your proportion of 2.36 over standard deviation of 0.019. And we should get a z-score of negative 1.89. So we're looking at the probability of a z-score being less than negative 1.89. Somewhere down here. We're looking at it being less. So this does kind of help verify our original answer, because we understand how much data lies below approximately 2 standard deviations of the mean for a normal distribution. And again, you can use normal CDF, lower bound something large, and negative, upper bound negative 1.89, mean is 0, standard deviation is 1, and you should get approximately the same answer, 0.029. We're doing this again because you never know what information you're going to be given, and you should be able to, whether you're given information partially from here or here, be able to bounce back between the two like we saw earlier in some practice. Okay, so now that we are done with those two examples, I would like for you to finish up example number 3 and example number 4 and have them ready to go in class on Friday. I'm going to be calling on people to get their answers for these problems, and we will go over them together to make sure you have a clear understanding of what is going on with sample proportions. Remember to be very neat with your notation. You can choose which one you like and what you feel comfortable with as we go forward. This will begin to become like second nature to you. So do your best. Don't forget to check your conditions, and we're going to go over these in class on Friday. Have a wonderful Wednesday.